Good days, respected lecturers and fellow friends. Today, our group will be presenting project title Digital Process Troubleshooter for Centrifugal Pumps, Bridging Numerical Methods and Industrial Optimization. My name is Li Pei, and together with my teammates, Maisar Alia Faikabibi Ramzi and Muhammad Muas bin Muhammad Farid, we developed a MATLAB application that helps engineers diagnose centrifugal pump performance using numerical methods. Throughout this presentation, we will explain the engineering problem, the numerical methods we apply, and how our application works, and the result of them from our study. Centrifugal pumps are among the most widely used equipment in chemical plants. In fact, they account for approximately 20% of industrial electricity consumption worldwide. However, many pumps do not operate at their best efficiency point or BEP. When this happens, energy consumption increases while efficiency decreases. At the same time, excessive vibration and mechanical wear shorten the lifespan of the pump and increase maintenance costs. Therefore, we developed a digital troubleshooting tool that allows engineers to quickly identify inefficient operating conditions and recommend corrective actions before serious failures occurs. Slide illustrates why operating away from the best efficiency point is dangerous. At the BEP, the pump operates with maximum efficiency, minimum vibration, and the lowest energy consumption. If the operating point shifts to either the left or right of the BEP, hydraulic losses increase. As a result, the pump experiences higher vibration, bearing stress, seal damage, cavitation risk, and unnecessary power consumption. Therefore, one of the primary objectives of our application is to determine the operating point and evaluate how far it deviates from the BEP. Our case study focuses on a chemical processing plant where a centrifugal pump transports cooling water from storage tank to an elevated heat exchanger. Recently, plant operators observed increasing electricity consumption together with a reduction flow rate, indicating that the system may no longer be operating efficiently. The engineer must determine the actual operating flow rate, calculate system head, evaluate plant efficiency, identify the deviation from the BEP, and finally recommend suitable corrective actions. Our application performs all this analysis using numerical method. The process begins with the input interface, where users enter pipe dimensions, fluid properties, static head, operating conditions, and the pump performance data. Next, the mathematical engine processes the data using several numerical methods, including polynomial regression, Newton-Raphson method, and the optimization technique. Finally, the diagnostic intelligence evaluates the operating condition and generate recommendations such as adjusting pump speed, throttling the valve, or improving the maintenance. At the same time, the application displays graph and performance indicator to help engineers visualize the pump behavior.
Good day everyone. Today I'm excited to walk you through our advanced pump analysis application and explain the core data processing pipeline that powers it under the hood. Our system operates on a clean 5-stage agricultural pipeline designed to take raw data and turn it into the actionable engineering insight. First is ingest. We begin by pulling in raw Excel performance data alongside specific user inputs. Second, model. We then apply polynomial regression to smoothly fit the manufacturer discrete pump curve. Third, solve. Next, a custom Newton-Raphson solver step in to pinpoint the exact operating intersection between the pump and the system. Fourth is optimize. We run a high-resolution grid search to locate the absolute best efficiency point or BEP. And finally, our fifth is app. Finally, the app generates real-time output calculation and automated diagnostic logic to guide operators on the factory floor. Before we dive into the graphic, let's look at our numerical toolbox. The backbone of this application relies on matching the right mathematical method with robust engineering justifications. As you can see from this metric, we use a second-order polynomial regression because a continuous quadratic fit minimizes the data fitting errors from the scatter manufacturer data. Our Newton-Raphson method gives us rapid quadratic converge to find the exact system operating point using numerical derivative. For finding the BAP, a grid search of 1000 point resolution guarantees high accuracy. And to calculate the Darcy friction factor, we implement the Swami-Jain approximation. This implicit formula completely bypasses the heavy, computationally expensive iteration required by the standard Colebrook equation. Let's look closer at method 1, polynomial regression. Manufacturer pump data is notoriously discrete. It's just a collection of scattered points on a page. To perform reliable calculus, optimization, and root findings, the app utilizes least square fitting to translate those scattered points into a continuous, highly predictable mathematical functions. This gives us a mathematically sound curve to work with moving forward. Moving on to the system resistance. To find out how the system behaves, we must calculate the dynamic friction head loss, which requires the Darcy friction factor. As mentioned, the standard Colebrook equation requires the intensive iteration. Instead, our application implements the explicit Swami-Jain approximation. This allows the application to achieve an impressive 1% accuracy for turbulent flow while keeping the computational overhead incredibly light. Once we have the pump curve, the system curve, we need to know exactly where they meet. So this brings us to the method 3, the Newton-Raphson solver. So we use the mathematical condition that we are solving for. So the app starts with a mean flow rate guess. It is then applies a numerical derivative via a tiny perturbations, where delta Q is equal to 0.001 and rapidly iterates through guess 1, guess 2, and guess 3. Within fraction of a second, is locked onto the exact operating point. To effectively diagnose system inefficiencies, we first have to define what perfection look like for our pump. Method 4 focus on high-resolution BEP optimization, so the app deploys a fine 1000-point grid search directly across the calculated efficiency curve. So by scanning this high-resolution spectrum, it reliable isolates the absolute maximum efficiency point, or we call as the QBP. Everything we just discussed is packed into this clean user-friendly interface. On the left, you have the input panel. This is a centralized space to enter pipe geometry, fluid properties, and import raw performance data directly from Excel. In the center, our visualization should provide three dynamic axes display the pump versus system curve, the efficiency curve with the BEP clearly marked, and the power curve. On the bottom right, the result and diagnostic panel translate the math into real-world choices. It pairs real-time readouts of a traffic light, status lamp, and an automated recommendation box. In this example, it warns the user that the pump is operating away from the BEP and explicitly advises adjusting the pump speed or throttling the valve. To wrap up my part, let's take a quick look at how this executes under the hood in the source code. In the top code of snippet, you can see the precise script calculating the Reynolds number and translating the Swami-Jain formula into a single line of explicit code, avoiding loop overhead. And in the bottom snippet, you can see our integrated numerical optimization routine, and it's generate a fine grid using lean space up to 150% of maximum flow loops through those 1000 points. Calculate the efficiency each step, and use a standard tracking conditional to smoothly log onto the maximum efficiency and isolate the precise QBP flow rates. And this combination of efficiency physics modeling and smart numerical optimization result in a tool that is both highly accurate and lightning fast.
So this is the app simulation. We input all the data into the column and we export the data from the Excel and we press run and then we will get the data. So this is the app simulation. We input all the data into the column and we export the data from the Excel and we press run and then we will get the data. So this is the app simulation. We input all the data into the column and we export the data from the Excel and we press run and then we will get the data. So this is the app simulation. we input all the data into the column and we export the data from the Excel and we press run and then we will get the data. So this is the app simulation. We input all the data into the column and we export the data from the Excel and we press run. Next, we go to real world application system regression. So, the scenario given a chemical processing plant transporting cooling water to an elevated heat exchanger show increasing energy consumption and reduced flow. So, by using the app, we can diagnose the current performance and recommend the corrective action. So, by using the given parameter, which is pipe geometry, fluid specs, system state, we all input all the data into the app. So when we input all the data into the app, we will get two curves. First curve is pumps versus system curve. The next one is efficiency curve. So from the pump versus system curve, we will get the operating point, which is Q equal to 116.7 meter cube per hour and the H is 12.38 meter. Next, we get the efficiency curve. The current efficiency is 78.75% and the BEP, QBEP will get 79.3 meter cube per hour. So the efficiency at QBEP is about 84%. So we get a diversion about 37.4 meter cube per hour. The current operation is fundamentally misaligned with mathematically optimum. Next, we go to the cost of BEP operation. So there are three main causes of BEP operation. The first one is energy penalty financially. So it's about 31.5 kilowatt being consumed per 8-hour shift versus 29.2 kilowatt per hour at BEP. So it has a 6.7 power penalty causing about 335 loss annually for this single pump only. So the next one is mechanical stress. Increased radial thrust on bearing due to the off-off BEP operation and elevate vibration risk severely threaten mechanical seal. The next is system stability. High calibration risk due to the NPH requirement at elevated 116.7 meter cube flow rate. Next, we can do an automated diagnosis logic. There are three tiers that can be classified. The first one is red one is critical, which is efficiency is lower than 17%, shows a low efficiency and the system is critical. So the action needed is inspect pump wear and check impeller fouling. The next one is yellow warning. Pressure drop is lower than 15 or BEP diversion is below than 5 meter cube per hour. So this shows a high pressure drop or operation away from BEP. So the action needed is check pipe blockage, adjust pump speed or throttle valve. So this is our case. The next one is the green one, which is healthy. The all other parameter are normal. The system healthy and optimized, and the action needed is maintain operation near BEP. Next, we evaluating the digital engine. So using the parameter which is operating flow, system head, pressure drop, and power. We compare with manual calculation and the app result. So we will get the relative about 0.17, 0.24, 0.51, and 0.3. So all this relative is below than 0.055%. So the digital solver match reduces manual engineering calculation with zero human fatigue. So for our case study, we will get the diagnosed data which is operating flow is 116.7 meter cube per hour. The system efficiency is about 78.75%. The BEP direction is 37.4 meter cube per hour. So the status of the system is yellow, which is warning. So pump is operating significantly far from ideal BEP flow, which is 79.3 meter per hour. Elevated flow rate is causing unnecessary mechanical stress and energy penalties. Next, we can calculate the financial cost of efficiency. So our current energy being used is about 31.5 kilowatt per hour, and versus the optimal one, we use about 29.2 kilowatt per hour, the optimal one. So it's about 2.3 kilowatt per hour being waste per shift. So at zero point 0.4 kilowatt per hour ringgit, this derivation costs about 335 ringgit annually for this single pump. In a chemical plant, running 100 pump optimizing 2 BEP recovers 33,500 per year, directly to the bottom line simply by adjusting the operational parameter. So there are three strategies that can be done to fix our pump. The first one is throttling. Action partially close discharge valve. The cost is very low. The system impact quick shift to lower flow but introduce artificial resistance. The next one is VFD installation. We install variable frequency drive. The cost is very high. System impact reduce pump speed to match BEP dynamically. Highest long-term ROI. So the next one is impeller trimming. The action is physically reduce impeller diameter. The cost is medium, but the system impact is permanent capacity reduction for consistently lower flow demands.
Next, I would like to discuss some challenges we encountered during the development of our application. The first challenge was the convergence of the neutral reaction method. This numerical method is very sensitive to the initial gas, and a poor starting point can cause the solution to diverge instead of converging. To overcome this issue, our application automatically uses the mean flow rate from the pump data as the initial gas. This provides stable starting point and ensures reliable convergence for most operating conditions. The second challenge involved calculating the derivative provided by the neutral reaction method. Deriving the mathematical expression analytically would make the algorithm more complicated. Therefore, we implemented a numerical derivative using a very small perturbation, delta Q equals to 0.001. This approach simplified the implementation while maintaining sufficient accuracy for engineering applications. Besides from solving engineering problems, our project also supports sustainability and future technological development. From the planetary health perspective, improving pump efficiency helps reduce unnecessary electricity consumption. Even though our test case show only about 6.7% energy penalty, when similar improvements are applied across thousands of industrial pumps, the total reduction in energy use and carbon emission becomes significant. Looking ahead, we have proposed three major improvements. First, replacing polynomial regression with cubic spline interpolation for more accurate pump curve modeling. Second, including minor loss calculations such as losses from valve, fittings, and pipe entrance. Finally, extending the applications to support multiple pumps operating in series or parallel, making it suitable for more complex industrial systems. This slide summarizes our future development roadmap. The first improvement is advanced modeling, where quadratic polynomial fitting will be replaced with cubic spline interpolation. This provides better accuracy, especially for highly nonlinear pump curve. The second stage focuses on micro-efficiency by replacing the current weak search with the golden section search algorithm, allowing faster and more efficient optimization of the best efficiency. The third stage introduces holistic system realism by incorporating minor losses caused by valve, elbows, and fittings into the system head calculation. Finally, the fourth stage is network pumping, where the application will be expanded to analyze pumps operating in series and parallel configurations, making it suitable for larger industrial plants. This diagram illustrates how numerical methods can create impacts at different levels. At the micro level, Numerical optimization identifies the most efficient operating point, helping minimize power consumption and energy waste. At the meso level, predictive diagnostic allows engineers to detect problems earlier, extending equipment lifespan and reducing maintenance costs and material waste. Finally, at the macro level, when these improvements are implemented across industry, they contribute to the sustainable development goals by lowering industrial energy demand, reducing greenhouse gas emission, and protecting both local communities and the environment. This shows that the numerical methods are not only mathematical techniques, but also practical tools for achieving sustainable engineering. To conclude, our digital process troubleshooter demonstrates how the numerical methods we learn in class can be transformed into a practical engineering solution. By integrating polynomial regression, the Newton-Raphson method, and optimization technique, our applications help engineers analyze ground performance, diagnose operational problems, and recommend effective solutions. More importantly, this project shows that the applied numerical methods are not just academic concepts. They play an important role in improving industrial reliability, reducing operating costs, increasing energy efficiency, and supporting environmental sustainability.